Hello students, welcome to this next lecture of the second chapter lathe machine, and in this lecture we will discuss about taper turning and its different methods. So to understand different taper turning methods, let us first of all understand what is the meaning of taper and taper turning. So normally if you see any of the flat component is having uniform thickness or width. But whenever there is a reduction or a gradual reduction in the width or thickness, then the shape may result as like this. So the reduction of the flat component or the gradual reduction of the flat component in width or thickness direction, so the final component obtained is called as the tapered component. So this component is called as the tapered component, and the process with which this component is made tapered is called as the taper turning process. So simply, if we define, taper turning is nothing but the gradual reduction of the component in length direction, in width or in thickness. So let us consider some of the important terms that are required to understand the taper turning methods. So look over here, there is one tapered component is shown, and in that let us give some of the names. First, if this is the larger diameter of the component, then it is indicated as capital D, and this capital D is nothing but the larger diameter. Now on the another side, this is the small diameter D, so it is nothing but the smaller diameter of the tapered component. Similarly, let us consider it as length, and this is the length of the component. In some of the books it is indicated as capital L, in some of the books it is indicated as the small l, but based on your convenience you can indicate it as capital L or small l, but based on that you need to formulate the further equation that we will discuss. Now similarly, you can see over here, if we draw a horizontal line from the smaller diameter towards the larger diameter, what happens? There is some angle you can see, if we indicated is angle alpha, and on both sides this is the same angle which is indicated as the alpha. So this alpha is nothing but the half taper angle. It is indicated as half taper angle, and if we extend the conical end, you can see that from both sides this is half angle, this is half angle alpha, so the full taper angle is indicated as 2 alpha. That means this 2 alpha, that is nothing but the full taper angle. So again, the main notation that we have given to this particular component is, first one is capital diameter D, that is the larger diameter of the tapered component. Small diameter D indicates the smaller diameter of the tapered component. Another one is the length of the component, and this alpha indicates the half taper angle, and 2 alpha indicates the full taper angle. And from this all notation that we have given to this component, now we will understand the another important terminology, that is the conicity. So what is the conicity? Conicity is nothing but the ratio of diameter of the tapered component to the total length of the tapered component. That means capital D minus small d divided by the L, and this conicity is also indicated as K. That means this conicity gives the relationship between the diameters of the tapered component and the length of the tapered component. So keep this particular definition in mind, because this definition will be helpful, or the meaning or formula of this conicity will be helpful to you in further formulas that we are going to derive. So I hope you got the clarity about what is the tapered component and what are the important notation that are required to understand further topics. Now let us write this conicity equation at another location and we will continue our derivation. So again, conicity, that is equal to capital D minus small d divided by L equal to K. And now we will derive the further equation using the another terms that are given. So for this again let us write, this is the capital diameter D, this is the smaller diameter D, and now as you can see from both sides the distance over here is similar. So the distance is similar from the both side and let us indicate it as small x. And now you can also see that at this particular location, if we draw a horizontal line, so this angle is nothing but the angle alpha. And let us give the name to this triangle, triangle A, B, C, and this is the right angle triangle. So over here, if we write the capital D, that is equal to, so this is the capital D, and capital D equal to, we can write the summation of all these terms. That means capital D, that is equal to x plus D plus x. That means capital D, that is equal to 2x plus D. So we can write D minus D, that is 2x. So x, that is equal to capital D minus small d divided by 2. So this is the value that we can get using simple mathematical terms. And again, if we write for the triangle ABC, so let us write for the triangle ABC, we know that over here this AB indicates the length of the tapered component. That means this AB is nothing but the small l. Similarly, this BC is nothing but the x. So this indicates the value x. And over here at the point A, angle made is alpha. So at this point, this is the angle alpha. So now if we use the sine formula or the cosine formula for this particular triangle ABC to consider all the dimensions that are required. So for that, if we write tan alpha, so tan alpha is nothing but the BC divided by AB, and the value of BC, that is equal to x, and the value of AB, that is equal to L. So over here we can write tan alpha, that is equal to, what is the value of x? The value of x we can get from this particular equation. That means tan alpha, that is equal to capital D minus small d divided by 2L. So this gives the relationship between the taper angle and the diameters of the tapered component and length of the tapered component. So this equation gives the entire relation between all the notations that are available in the tapered component. Now if we want to write this particular equation in the form of the conicity, for that you just need to consider the equation of conicity that we have written over here. So we know that capital D minus small d divided by L, that is equal to small k. So from here we can write the equation as tan alpha, that is equal to, now in place of d minus d divided by L, what one can write? One can write d minus d divided by L, that is equal to conicity k. That means that is k divided by 2. So this gives the relationship between taper angle and the conicity term. So from these particular derivations we have got the relation in three different forms which will be helpful to you in further derivations. So let us write all that equations that are helpful to you in further topics, that are the first one, that is the conicity. Conicity, that is equal to capital D minus small d divided by L, that is equal to k. Another equation that gives the relationship with taper angle, so that is tan alpha, that is equal to capital D minus small d divided by 2L. And the relationship between these two terms that can be indicated as tan alpha, that is equal to k divided by 2. So you can write k, that is equal to 2 tan alpha. So these are the three equation 1, 2 and 3. These three equations are important to you for calculation purpose also and for our further topics also. So keep this in mind, all these three equations. Now as we have discussed about what is the taper, now how to calculate this taper angle and what are their relationship. But to generate this particular taper, there are different methods are available for these machineries. So all that different methods are, the first one is tailstock set over method. Now the another one, that is the swiveling compound rest method. Now the third one, that is the taper turning attachment, and the fourth one, that is the form tool method. So from all these four methods, the first two methods are very much important to you for examination point of view also. The first one, that is the tailstock set over method, and the second one, that is the swiveling compound rest method. So now we will start our discussion with the tailstock set over method. Now to understand what is the tailstock set over, so for that just you need to consider a simple term. Now let us show over here, if this indicates the location of headstock. So if this is the headstock and parallel to this, as we know, another part is available of the lathe machine, that is the tailstock. Now headstock and tailstock are available parallel to each other and in a single line. But now as we fix the component between headstock and tailstock, what happens? The component is fixed between this headstock and tailstock. And now if we want to generate a taper on this component, we must need to provide a certain angle. So to provide that certain angle to the component, this tailstock is shifted perpendicular to its location to another location, and as there is a shifting or the setting over of the tailstock to this another location, what happens now? Component to be fixed is now setted as the direction shown over here. So this way the another component is setted, and here the certain angle, at a certain angle this component is setted, and that angle is nothing but the required taper angle. So this tailstock is setted to another certain location, and this distance up to which this tailstock is moved, that distance is indicated as S, and it is known as the set over distance. So it is called set over distance. So now I hope you got the clarity what is the meaning of tailstock set over. Shifting the tailstock to the perpendicular to its plane, that shifting is nothing but the set over distance. Now how this set over distance will be helpful to generate the particular taper that we will discuss now. So for that, let us have a look at the figure shown over here, and let us first note the important terms. So over here, this indicates the larger diameter of the tapered component. Small d indicates the smaller diameter of the tapered component, and over here the entire length of the component is indicated as the capital L, whereas the tapered length of the component is indicated as the smaller l. And the tailstock is shifted from its original location to a distance s. So this distance s indicates the set over distance. So now if we draw the triangle, now if we, here this makes the angle alpha with the horizontal, and if we draw the perpendicular from this particular plane, and let us give the name to this triangle. So this triangle is A B C. So, and the angle made at this particular point A, that is the angle alpha, that is the taper angle. So for this angle, let us draw this particular triangle to another point. So if we draw over here, so this is the point A, point B and point C, and the angle made it is alpha. Now what is the distance over here? This distance AC, that is nothing but the full length of the component. So this distance AC is nothing but the capital L. Similarly, this distance BC is nothing but the set over distance S. Then this distance BC, that is the set over distance S. Now if we write the particular use, or we use the sine rule for this particular triangle, then the formula will be sine alpha, that is equal to, now as the angle is available at point A, so the sine alpha equation will be BC divided by the hypotenuse, that is the AC. So the value of BC is set over distance S, and the value of AC, that is the total length of the tapered component. Now for the very small angle, the value of sine alpha is nearly equal to value of tan alpha, and this you can check by using a simple example. You can find in your calculator the value of sine 0.005 degree, and also you can find the value of tan 0.005 degree. The value of both these will be nearly about similar. So that's why we can write sine alpha, that is nearly equal to tan alpha. So here now the equation becomes tan alpha, that is equal to S divided by L, and as we know, S, that is equal to tan alpha multiplied by L, and the value of tan alpha that we have derived in our past formulas. So the value of tan alpha, that is nothing but the capital D minus small d divided by 2L. So at the point of tan alpha, you can write the same values over here. So S, that is nothing but the capital D minus small d divided by 2L multiplied by the L. So this formula gives the relationship between set over distance and the different terms that are available in the tapered component. So let us again write this formula, and we will discuss this another important parameter that we can derive from this formula. So now what is the equation for set over distance? So the equation for set over distance, that is d minus d divided by 2L multiplied by the capital L. Now this is the basic equation, right? And now if we say the taper to be generated is entirely over the overall length of the component, that means tapered length is equal to the total length of the component. So at that time the set over distance becomes d minus d divided by the 2. So this is the another equation that you can derive from this basic equation. So we have up to now derived many different number of formulas which will be helpful to you during calculation of examples also, and these you can also use during the derivation purpose. And this particular method, as we have discussed, this particular method is helpful only when the taper to be generated is very small and the workpiece is longer in length. So this tailstock set over method is useful when longer workpiece is available and angle to be generated that is smaller. That means smaller taper angle to be generated. At this particular time this tailstock set over method is used. So now we will list all the formulas that we have derived up to now. The first one, that is the formula for conicity. So formula for conicity, that is equal to difference in diameter divided by the length, and that is equal to K. Now the second formula that we have derived, which gives the relationship between taper angle, that is capital D minus small d divided by 2L. Other than that you can also write K divided by 2. And the third equation, which we have obtained by using the set over distance, so that is set over distance S, that is equal to capital D minus small d divided by the 2 L into capital L. And the next equation, that is nothing but the S, that is equal to, over here we have written capital D minus small d divided by 2L into L. But when the tapered length and the total length of component is same, at that time we can write the set over distance as D minus D divided by the 2. So these are the different equations which will be helpful to you during examination purpose also. Now again we will discuss about the another method that is helpful for taper turning. So another method, that is the taper turning by swiveling compound rest. Now in this method the important terms are, at this particular location this round plate is known as swiveling plate. Another one, that is the compound rest, which is rested over it, and this particular wheel is called as the compound rest wheel or the compound rest feed screw. So here in normal condition what happens, this particular tool is available in this direction and this is the compound rest. Now what happens during the taper turning, whatever the taper angle is required, suppose if the taper angle that we need to generate, that is the alpha, then what happens, we must need to rotate this particular tool by angle alpha. So this tool is given a rotary motion by angle alpha by using the swiveling plate. And on this swiveling plate certain angles are indicated using which you can easily rotate the particular tool by certain angle. So using this swiveling plate this entire compound rest is rotated by angle alpha, and as the rotation completes the compound rest, you can see like this. So this indicates the location of compound rest. Now after adjusting the taper angle, what happens, this tool is given feed movement in particular direction as we want to generate the taper angle. And after providing a depth of cut up to certain depth, we need to cut that particular component, and after providing that depth of cut, what happens, we are providing the feed along the length direction by using or by rotating this compound rest screw. When we rotate this compound rest screw, what happens, this tool moves from one point to the another point. Now after completion of the first turning operation, further we are taking away this particular compound rest, and again we are providing the depth of cut to this particular workpiece using providing this tool, and now again we are providing feed in length direction using this compound rest feed screw. So the movement of this compound rest feed screw provides the feed and removes the material, and at the end of the machining we can obtain the tapered component like this. And in this particular method we are rotating this compound rest using the swiveling plate, and that's why this method is called as the taper turning by swiveling compound rest. So in this method there is a simple logic is available. Whatever the angle we need to generate, that by that angle or by that amount we just need to rotate the tool, and after rotating that tool we are providing feed using the compound rest feed screw, and at this particular location there is no any other calculations are required. And using this compound rest screw, one can generate the angle from 0 degree to 45 degree. In this particular range, the taper angle can be generated using this taper turning swiveling compound rest method. So in this particular lecture we have discussed about the main important two methods, that is the first one is tailstock set over method and the second is swiveling compound rest method, and these two methods are helpful to generate the taper on the component. So I hope you got the clarity about what is the taper turning, what are its different method, and how taper can be generated using this lathe machine, and what are the different calculations are required. So looking forward to see you all in our next lecture. Up to then, thank you.